Hi everyone, in this video we look at the mechanism for the hydroboration step of the hydroboration oxidation reaction. Before we jump into the curved arrows, let's take a look at the experimental results that we're hoping to explain, both the regio and stereochemical outcomes. We start with an alkene, and in step 1, we react with borane and THF as the solvent. 3 equivalents of our alkene, that is 3 alkenes combined with 1 borane to produce this trialkyl borane. These 3 butyl groups come from butene. Notice that this boron atom adds to the less substituted side, whereas the hydrogen adds to the more substituted side. This corresponds to an anti-Markovnikov addition or non-Markovnikov addition. The second step, 2, involves hydrogen peroxide in base with water. This is an oxidation step that oxidizes the trialkyl borane to produce alcohols. The alcohol replaces the boron and so remains at the less substituted site. In the example below, we show 1-methylcyclohexene reacting under the hydroboration oxidation conditions to give an alcohol product. This alcohol again adds to the less substituted site, but here, because we produce 2 chiral centers, we can see the stereoselectivity, that this is a syn addition. Both the H and OH have added to the same side. We also get the enantiomer here. So we get selectivity for a pair of enantiomers out of the 4 possible stereoisomers. In addition to the experimental data presented here, we also do not observe any rearrangements for this reaction. So given the observed stereoselectivity as well as the lack of rearrangements, carbocations must not be intermediates in our reaction mechanism. With all that in mind, let's start drawing curved arrows. As we are focusing on the hydroboration step of the hydroboration oxidation reaction, we're going to focus on how the alkene reacts with borane, because that's where the regioselectivity is set as well as the stereoselectivity. We have borane drawn out here as its Lewis structure as well as the alkene. Which of these 2 species will serve as the electrophile in our reaction? Borane will be the electrophile here. Remember that electrophiles are electron-loving and themselves are deficient of electrons, having a full or partial positive charge. To find these positive charges, we must look to the bond dipoles. Hydrogen is more electronegative than boron, so boron will have the partial positive charge in borane. Borane's reactivity as an electrophile can also be supported by the octet rule. Borane is one of those exceptions where it forms 3 bonds, giving it 6 electrons in its valence shell. It really wants to have 8, so it reacts pretty readily to gain those 2 electrons. In fact, it is the solvent THF that stabilizes borane. Borane is very reactive, and the solvent serves to stabilize it. The lone pair gets added to the boron, so we have this borane THF complex that is our source of borane in the reaction. Alkenes are electron-rich, and this pi bond is a region of electron density that will serve as our nucleophile. So the nucleophile attacks our electrophile. This forms our carbon-boron bond. At the same time, it's proposed that this hydrogen atom forms a bond with the other carbon of the alkene. So we are forming both the carbon-boron bond as well as the hydrogen-carbon bond simultaneously. This concerted one-step reaction mechanism explains the syn stereoselectivity of our reaction. It is just not geometrically possible for these 2 groups to add to opposite faces in one step. We get a pair of enantiomers ultimately at the end. The enantiomer of this is formed as well. We get this pair of enantiomers because the alkene is planar. The borane can add from the front face of that alkene, or it could add from the back face with equal probability. In order to explain the regioselectivity of this reaction, we must look to the transition state structure to see where partial charges are developing as bonds are breaking and making. And that transition state is the high energy point on our reaction coordinate diagram from reactants to products. It gives us a snapshot of those bonds breaking and forming. Here on structure A, this is transition state A, we could imagine that as this pi bond is breaking and the carbon-boron bond is forming, we are developing partial positive charge at the more substituted site here. While at the same time, this boron-hydrogen bond is breaking. Hydrogen is developing some anionic character because it's gaining electrons from the boron faster than this carbon-hydrogen bond is forming. Okay, so we have positive and negative attract here. In scenario B, we have the opposite happening. The pi bond is breaking as the carbon-boron bond is forming, but we've just flip-flopped things. So now the cationic character is on the less substituted side of the former double bond. Which transition state structure do you believe is more stable based on the placement of that cationic charge? Carbocations are more stable with more substituents due to inductive effects that stabilize them. So having this partial positive charge on a more substituted carbon is going to be more stable because these alkyl groups can serve as donors and stabilize that partial positive charge. Because this charge is less substituted, it would then be less stable. There's a second factor at play that we can use to explain why transition state A is lower in energy. This borane is a larger group and in this structure is farther from the alkyl substituent up here. So we've got a steric interaction that is minimized in transition state A, whereas these two larger groups are closer together in structure B. So between this combination of electronic effects, where my charges are, and steric effects, where my bulky groups are, we can explain that transition state A is lower in energy. This will be the fastest pathway to my major product and give us the regioselectivity that we observe having the OH on the less substituted carbon of my former alkene. This mechanism explains both the stereo and regioselectivity of our reaction. Thanks for watching.